So I guess I'll continue with the fermionic path integrals. And I was saying last time that it was curious that we simply picked a state that was annihilated by the fermionic operators. Well, anyway, we'll get to that in a moment. So suppose we have several Grassmann variables. And the complex conjugate versions as well. And that we have fermionic variables and the adjoints of those as well. In fact, I was writing them as adjoints. And these guys all anti-commute. The theta I, theta j is 0, and theta I, theta j star anti-commute. And of course, starring this, you get the theta stars anti-commute as well. In the case of the actual fermionic operators, what we have is delta ik, and on the other hand, psi I, psi k, anti-commutator is 0. And what we do is we define our vacuum state as a product over all of the fermionic variables on a state S, where S is a state that is not annihilated by every one of these fermionic operators. And as I was saying last time, this shows you that this state S is quite arbitrary. On the other hand, when we talk about fermionic variables in an ordinary course in quantum field theory, all we say is that we have a state that is annihilated by the annihilation operators, and we don't worry about whether the state is unique. In the case of bosonic field theories, one can, I suppose you're just doing quantum mechanics. If you have a single harmonic oscillator, you can show that there's a unique ground state, of course.
And so here we don't need that. We just, like you said, we just need that at least one of those psi k operators does not annihilate S.
We want that all of them don't annihilate
So
S.
none of them, all
Yeah, because if any of them did, the state would
the
vanish.
whole thing goes away. But we could
Yeah.
have.
So,
I see. That makes
but
sense.
I suppose that what one can show is that in the fermionic space, it's a unique state, I imagine. I imagine that one can show that without a great deal of difficulty. But it is a little puzzling at first sight. So we define coherent states or eigenstates of these annihilation operators as E to a sum on K from 1 to N, psi K dagger theta minus a half theta K star theta K. And I left the K out there, off there. And that is on the state 0. And this is very similar to what we do in ordinary coherent states in the bosonic case. In the bosonic case, what we do is we say this would be e to the ak dagger alpha k minus a half alpha k absolute value squared acting on the bosonic vacuum. That would give the coherent state. And in the case of bosonic variables, ak alpha would be alpha k alpha. And in the case of fermionic variables, what we have is psi k on this theta k on this coherent state theta. And moreover, if we have psi k, psi l on theta, what we get is, oh, I wrote it backwards in the notes. So this is psi k theta l theta. And then this is minus theta l psi k theta. And so this is minus theta L, theta K, theta, and then inverting them once again, we get theta K, theta L, theta. So so a product of fermionic operators on a coherent state gives you the product of the Grassmann variables on the coherent state. That's for the annihilation operators, not for the creation operators. So it's the size, not the psi daggers. And since the fermionic operators commute, the eigenvalues, since the fermionic operators anti-commute, the Grassmann, their eigenvalues must anti-commute. And one way of saying that is theta L, theta K on theta is psi L, psi k on theta, and this is minus psi k, psi l on theta, and this is minus theta k, theta l on theta. So what we see is that the eigenvalues of a fermionic operator have to be anti-commuting variables, Grassmann variables. And if you find that puzzling, well, I do too. This whole business of fermions and spin 1/2 is just really puzzling. Of course, spin 1 is also puzzling. In fact, how these particles can have any spin to begin with is puzzling, and what is the spin is not really understood. Although if the field transforms a certain way, it has to have intrinsically some angular momentum. I don't know. Anyway, let's compute the inner product of two coherent states. Then what we have here is 0, and then we have a product, k equals 1 to n, expanding the exponential and taking the adjoint and so forth. We have 1 minus zeta k star psi k minus a half zeta k star zeta k, and that multiplies the product of, say, L equals 1 to n of 1 plus psi k dagger theta L. Whoops, this is an L. Minus a half theta L star theta L. Ground state. And then if you multiply that out, you can see that anytime the psi k hits the state on the right, the ground state on the right, you get 0. Anytime a psi dagger hits this one on the left, you get 0. And so what one gets here is simply exp of the sum on k from 1 to n of zeta k star theta k minus a half zeta k star zeta k plus theta k star theta k, which we can rewrite in a vector or matrix notation as e to the zeta dagger dot theta minus a half, well, zeta dagger zeta plus theta dagger theta. Okay, and the identity operator for this extended, this space of n fermionic variables and their adjoints is an integral of outer products of these coherent states, product k equals 1 to n, d theta k star, d theta k. The advantage of writing it this way is that you can change the order of this product, and it doesn't, and you don't have any sign errors. In other words, you can say d theta 1 star, d theta 1, d theta 2 star, d theta 2. This is the same thing as d theta 2 star, d theta 2, d theta 1 star, d theta 1. So if you combine these fermionic variables in pairs, then they commute with each other, and there's no, you don't have to keep track of the signs. And that's one nice feature of this formula for the identity operator. Now, what I'm about to do is the most important thing, or one of the most important things of Grassmann path integrals. Let's just think of a 2x2 matrix here. So A is a 2x2 matrix. And it's a complex matrix. Now, this theta dagger A theta, of course, is theta 1 star, A1 1, theta 1 plus theta 1 star, A1 2, theta 2 plus theta 2 star, A2 1, theta 1 plus theta 2 star, A2 2, theta 2. Okay, if we keep that in mind and stick it in the exponential there and then expand, what have we learned? Well, we learned that all the terms, in other words, this thing is integral e to the minus theta 1 star, A1 1, theta 1, oops, minus theta 1 star, A1 2, theta 2 minus theta 2 star, A2 1, theta 1 minus theta 2 star, A2 2, theta 2, d theta 1 star, d theta 1, d theta 2 star. Okay, now in this integral, the only terms that are going to survive are ones that have 1 theta 1, 1 theta 1 star, 1 theta 2, 1 theta 2 star. In other words, they have to be quartic in Grassmann variables, and you can't repeat any Grassmann variable. And the way this can occur, let's see, did I leave out a 1/2? No. This thing, the exponential is quadratic, so of course the first term is 1, that gives 0. The second term is quadratic in thetas, that gives 0 because we're integrating over 4 thetas. The next term is the square of what's in the argument of the exponential. That's quartic, that counts, and that's important. All subsequent terms in the exponential give 0 because they have 6 or 8 or more fermionic variables, and so somebody repeats because there are only 4 different fermionic variables. And so what we get is that this G of A is then an integral theta 1 star A11 theta 1 theta 2 star A22 theta 2 plus theta 1 star A12 theta 2 theta 2 star A21 theta 1 times d theta 1 star d theta 1 d theta 2 star d theta 2. Now, there are, of course, other terms that I left out, namely there's one that has this term on the left multiplying that, but in the second term there's a 1/2, and so the 1/2 cancels. And also there's a term where the 2 appears in front of the 1, and that one is the same as this one. And so you get this term twice, and that cancels the 1/2 in the expansion of the exponential. And so what you get then is A11, A22 minus A12, A21. And this is the determinant of the matrix A. So basically what we have is the integral of e to the minus theta dagger A theta let me just write this as d theta star d theta, where what I mean by that is that you multiply these out and you've got 2 of them. This is then equal to simply the determinant of A. And in fact, that's the general result. For an arbitrary number of variables, integral e to the minus theta dagger A theta d theta 1 star d theta 1 d theta n star d theta n is equal to the determinant of A. And what is interesting here is that if we were dealing with bosonic variables and you did the same thing, what you get is 1 over the determinant.
So that's interesting. That alludes to kind of like a symmetrization technique for Grassmann numbers.
I'm sorry, can you read that
This
again?
is like a symmetrization technique for Grassmann numbers. It's not relevant for fermionic properties, but just in general, in terms of Grassmann path intervals, this can be used to symmetrize because the only surviving terms you have are the terms that contribute to the 2x2 determinant. Right, because you have all those other zeros. I don't think this is important. It's just mathematically interesting.
Okay. Well, the thing that I just mentioned is one of the reasons why people like supersymmetry. Because in supersymmetry, then you have a symmetry between the bosons and the fermions in the theory, so you get a determinant of A in the numerator from the fermions you get a determinant of A in the denominator from the boson, and so some divergences can cancel. Now, there's another trick that's related to this, namely, suppose we do this: e to the minus theta dagger A theta plus theta dagger zeta plus zeta dagger theta, and we do this d theta 1 star, d theta 1, d theta n star, d theta n. So we do that integral. Now, what we're going to use first is the invariance of Grassmann integration under translations, and that is the property that we use to define Grassmann integration. And so we can replace theta by theta plus A inverse zeta. And so this is the same thing as e to the minus theta dagger A, but now this is theta plus A inverse zeta. And the next term is theta dagger zeta. We don't do anything to that, but in this term we shift theta, and so this is plus zeta dagger times theta plus A inverse zeta, and then we have product d theta star d theta. Now, what you can see is that this term is minus theta dagger zeta, and that cancels this term. So those terms go away, and what we have left then is e to the minus theta dagger A theta plus zeta dagger theta plus zeta dagger A inverse zeta. Now what we can do is shift zeta dagger. And so this is equal to e to the minus, we shift theta dagger. And so this becomes theta dagger plus zeta dagger A inverse, and then A theta plus zeta dagger theta plus zeta dagger A inverse zeta product d theta star d theta. And now this term that's zeta dagger A inverse, zeta dagger theta with a minus sign cancels zeta dagger theta, and what we get is an integral e to the minus theta dagger A theta plus zeta dagger A inverse zeta times product d theta star d theta. And now these guys are just spectators, the integrals over the theta and the theta star, and so that gives us the determinant of A times e to the zeta dagger A inverse zeta. So what we've got is a formula here, e to the minus theta dagger A theta plus theta dagger zeta plus zeta dagger theta d theta star d theta. That integral is then this. And this is a useful expression. And of course, in a sense, it's very much like completing the square. And and this completing the square is just an incredibly useful thing in mathematics and also in quantum field theory. When you complete the square in a high energy theory, we saw a few weeks ago that gives us effective quantum field theories at low energy, and I was doing the boson case. This same formula will give us effective quantum theories of fermions. Okay, so now I want to go to the continuum case. So we started out with 1 or 2 Grassmann variables, went to n Grassmann variables. Now we're going to go to infinitely many Grassmann variables. And so we're going to have a Grassmann field, chi m of x, chi n of x prime, and these anti-commutators are always going to be 0. And the same thing with chi m of x, chi n dagger of x prime. In fact, let's use a star because that's the way I've been thinking. When I've been using dagger here, I've been using the transpose just to implement matrix algebra. The star is the one that gives us a new Grassmann variable. And we'll also have fermionic variables, phi m of x and t, psi m of x and t, psi n dagger of, say, y and t. These anti-commutation relations are delta m n delta q of x minus y, which you've undoubtedly seen before. And psi m, psi n, these guys anti-commute no matter where well, at equal times. So xt, yt. So the important thing here is equal time commutation relations. So let me just write that down. Equal times at. And the reason for that, of course, is that if you have simple anti-commutation relations at one time, and you let one of the fields evolve, the field could evolve in a very complicated fashion in an arbitrary quantum field theory. And so this thing would be God knows what, and so the anti-commutator could be just anything. So you have to stay with equal times. All right, now once again we're going to define a ground state, and we're going to define it by saying that the product, it's a product over M just goes, actually, these M and N's just go from 1 to 4, because these are just Dirac indices, matrix indices. And these are space points. And so the product of M, X, let us say, times 0. So we find some state such that that is not equal to 0. And we use it to define our ground state. And now the ground state will be such that psi n of y at time 0 will annihilate the ground state, because this will be the same as one of these, and you'll have psi squared equal to 0. Notice that this is a little bit like what Dirac was saying is Dirac C way back, in the 1920s, which is almost 100 years ago. He was saying that the vacuum was really filled, and what he was doing was using essentially that relation. So we can also define coherent states in this general context. Now this is a Grassmann function. And we can say this is an exponential of an integral, a sum on m, psi dagger. Actually, I think the sum on m is a little distracting because this sum on m is just over the Dirac indices. There are only 4 indices, so I'm going to write it this way. So these things are Dirac spinors, or since we're distinguishing between, yeah, all right, I'll call them Dirac spinors, 4-component spinors in any case. And they're functions of space because we're doing everything at the same time. And then this is minus I chi dagger of x, chi of x. And this is integrated d cubed x. And all of that acts on our ground state. And another way, a briefer way of writing this is psi dagger chi minus a half chi dagger chi d cubed x on 0. So that's our coherent state. And now the utility of this definition is that if we have, say, psi sub I of spatial x times 0 on this fermionic coherent state, what we get is the ith component of the Grassmann function at the space point x as an eigenvalue. So that's a Grassmann eigenvalue, and this is a Grassmann eigenvalue equation, but it's a functional equation because chi is a function, or if you want, 4 functions. And now we can repeat the same thing that we had before, namely the inner product of chi prime with chi is e to the integral chi prime dagger chi minus a half chi prime dagger chi prime minus a half chi dagger chi d cubed x, all in the exponential. And the identity operator is an integral chi d chi star. I'm going to write it as d chi star chi. I think that's clearer than saying what I mean by d chi star chi. Is d chi 1 star, d chi 1. Well, this is really a product of all space and a product of, so to write this out maybe explicitly at least once, what this actually is, so it's a product over all of space of these 8 Grassmann integrals. I guess since this is fermionic, maybe I'll adopt the notation that's in the book or notes. because after all, there are an even number of these guys, so you can move them to the left or the right, and it doesn't make any difference, because there are 4 of them. So the Hamiltonian now for a free Dirac field is an integral over space of psi bar gamma dot grad plus m psi. That's the expression. And remember psi bar, this is psi dagger beta gamma dot grad plus m psi. And another way of writing it is b cubed x psi dagger I gamma 0 gamma dot grad plus m psi. So there are these various ways of writing it. And of course, the gamma matrices, or gamma A, gamma B, is 2 eta AB. And I have the feeling now that I left out the 2s. I'm writing that down sometimes. Eta, of course, is the normal space-time matrix metric, minus 1, 1, 1, 1 on the diagonal. Okay, so what we have then is psi on chi is chi on chi, and chi prime psi dagger is chi prime dagger. So now we can compute what the time matrix elements of the time evolution operator, namely chi prime e to the minus I epsilon, say, H0 chi, and we're imagining that epsilon is infinitesimal. And so what happens here is that from the left, chi prime gives us chi prime dagger, and from the right, chi gives us chi. And so this turns out to be chi prime chi times e to the minus I epsilon integral over space of chi bar prime gamma dot grad plus m chi. Right, okay. So that's what we get. And now, if we remember what the formula is for the inner product of chi prime with chi, and substitute it here, what we get is e to the integral. We get 1/2 chi prime dagger minus chi dagger chi minus 1/2 chi prime dagger chi prime minus chi minus I epsilon chi bar prime gamma dot grad plus m chi, and all that is cubed x. So it's just one long exponential. And now we can do for fermions what we did for bosons, namely, we can say, well, chi prime dagger minus chi prime, minus chi dagger, sorry. So that's chi prime dagger minus chi dagger is epsilon chi dagger dot. And we can say chi prime minus chi is epsilon chi dot. And then, so we've got an epsilon here, an epsilon there, and an epsilon. And so we can ignore anything of order epsilon squared. And if we do, what we get is e to the integral, well, we can pull out the epsilon. And we have 1/2 chi dot dagger chi minus 1/2 chi dagger chi dot minus I chi bar gamma dot grad plus m chi dq base. And the idea here is that we're imagining that chi prime dagger and chi dagger differ by only epsilon, which is this thing. And so we're ignoring the difference between them because we're multiplied by epsilon here. So to first order an epsilon, we can erase all the primes. And now, if we put together n of these, where n is 2t over epsilon, I did 2t minus t because I wanted things to be symmetrical, an integral from minus t to plus t. I don't know. That was probably a stupid choice. I probably should have just said t over epsilon. But I better continue to follow the notes, otherwise I'm going to make a lot of mistakes. So what we do now then is we take a matrix element of chi sub t, and this just means a Grassmann a coherent state labeled t. It doesn't mean that it's at time t, really. And then we have e to the minus 2it h0 and a chi labeled by minus t. And so this is going to be the product of n of these. And now these Grassmann things have the marvelous feature that they anti-commute, but quadratic forms commute, so we can just multiply all the exponentials together and we get one exponential of the sum. And so this gives us where did I, okay, hold on a second. What I forgot to say is that each time we do this, we're going to be inserting the identity operator in this form. So we're going to be inserting this 2n times, I guess, or 2n minus 1 times. Anyway, this is going to come in a zillion times, and we're going to have one of these, an identity, another one of these, and so forth. And what you get, if you put it all together, and I probably should have put in an extra equation here, but I didn't, what you get is an integral of e to the integral a half chi dot dagger chi minus a half chi dagger chi dot minus I chi bar gamma dot grad plus m chi. And now we're doing d4th x, and we have d chi star d chi, meaning we're integrating over all of space and over all of these n or 2n identity operators that we've stuck in, which involve integrals over Grassmann variables at all space points. Okay, now keep in mind that minus chi dagger chi dot is equal to minus I chi bar gamma 0 chi dot gamma. And so we can rewrite this exponential. The exponential is an overall factor of I, and we have minus chi bar gamma 0 chi dot minus chi bar gamma dot grad plus m chi d4 of x. And this becomes I integral minus chi bar gamma mu, well, I went to covariant derivatives by mistake, hold on. Okay. Now, what is puzzling me just a little bit here, oh yes, okay, so we had an I here because it came from e to the minus I epsilon h0. The I's here come from taking chi dagger and turning it into a chi bar. That tosses out an I gamma 0. And so there's an overall factor of I here. Now we can recognize this as simply I times the integral of the Dirac-Lagrangian, or action density, d4 of x. So altogether what we have is that e to the minus I, or actually 2I t h0 chi minus t to t is an integral e to the I integral Dirac's action density d4 of x d chi star d chi, and we're integrating here from minus t to plus t. So that's the formula, and LD is minus chi bar d mu gamma mu plus m chi. Okay, so this, and of course this is then the same thing. This is what Feynman wrote down as the basic path integral formula. This is the fermionic, purely fermionic case. Now, the next step is to go to time-ordered products. So I wanted to write I'm trying to write a calligraphic T, and I don't remember how to do that. So let me just write a big T. So let's remember what the time-ordered product is for two fermionic operators. So it's first of all theta of x01 minus x02 times psi bar of x1 psi of x2. But then we insert by hand an extra minus sign here. Minus theta x20 minus x10 psi of x2 psi bar of x1. So there's this extra minus sign, and it's because the Fermi field's anti-commute, and I guess one way of thinking about it is to imagine what this time-ordered product is when the two times are identical. Well, when the two times are identical, this would be psi bar x1, psi x1 from this term, and maybe we'd say this thing when the argument's 0, we'd give it the value of 1/2. And then it would be minus 1/2, and then over here it would be psi x1 psi. Well, I mean, these are times, so let me say this is x1 t, x2, but it's also, we're imagining it's the same time. And so this one would be x2 spatial t psi bar x1 spatial also t. So that's what this formula gives us with the extra minus sign. And now we realize, let's suppose the space parts are different. Then they anti-commute, we don't have to worry about a delta function. And so we get is psi bar xt psi x1t psi bar psi x2 t. So this minus sign came here, and if we throw that way, we get another minus sign, so we just get this. And so this is what we'd expect, namely that if we go to the same time but different space points, we just get the product of the two fermionic operators, and if we wrote them in the opposite order, we'd get an overall minus sign. And so this would be the same thing as minus psi of x2t psi bar x1t. Okay. So that's why we insert by hand an extra minus sign into the fermionic time-ordered product. All right, now let's see, where was I? So if we now go to, we imagine maybe, well, I don't want to have you move the camera around. What we're going to be doing is essentially, suppose we want to take a time-ordered product of psi bar x1 ... down to psi of x2n. So what we would do is we would want to take something like this. Well, I've gone immediately to the vacuum from, let's maybe first consider just some chi t and some chi minus t, what these would be. Well, we would have something like this, but we want to stick these fermionic operators in at various points here. So it would be, for example, chi sub t e to the minus 2, well, e to the minus, it would be some time interval. So I delta t, I'll just call it h0, and then the first of these, which would be, let us say, let's suppose the order is this way. So we put the latest one sidebar of, say, x1 there. Then we'd have another e to the minus I delta t h0, and we might have a psi of x3 there. Who knows? And then an e to the minus I delta t h0, so forth, psi x, sidebar x4, and so on and so forth, down eventually to chi minus t. So that's what we're computing if we're just taking a matrix element. And now, when we insert identity operators, which are outer products of Grassmann coherent states, we insert them everywhere, and we expand this thing, which is delta t, where delta t is a finite time interval. We insert, we turn that into that. Altogether, what we get here then is chi sub t an integral e to the I, what do I call it, S0 for the Dirac action, and then these would turn into Grassmann eigenvalues or eigenfunctions, effectively. Well, eigenfunction values or eigenfunctions, I don't know. Anyway, it would be chi bar of x1 down to chi of x2n, and it would then be d chi star d chi, and that in fact would be what we'd get. And then what we would do in order to cancel the matrix element on the outside and to get down to an actual vacuum, it turns out that we would get this as the formula. It would be psi bar x1 dot 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 psi of x2n would then be a ratio, and it would be chi bar x1 dot 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 chi x. Gee, I've got chi bar and x being almost the same. Hopeless. E to the I S0 d chi star d chi, and then this would be divided by e to the I S0 d chi bar d chi. So it would be a ratio of path integrals, and in fact, in this procedure, what we would have is that there'd be an I epsilon appearing here, and the I epsilon would appear in such a way as to so that when we computed two-point or endpoint functions with that, we'd wind up using a Feynman propagator with the I epsilon in the right place in the denominator. And in fact, well, we have some board left. So what one would do now is to introduce a Grassmann current, and that would be 0 time ordered product e to the integral zeta bar psi plus psi bar zeta e4 of x vacuum. So we would be computing this quantity, and just as the mean value in the vacuum of a bunch of fermion fields turns out to be the fermion fields, but weighted by the phase of the action, this would turn out to be a ratio of e of an integral e to the integral zeta bar chi plus chi bar zeta plus L0 d fourth x, and then d chi bar, t chi star d chi, and then that will be divided by integral e to the I. Well, I can just write it. I don't know which way you prefer writing it. It should be an I here. So let me write it the same way. Integral L0 d fourth x d chi star d chi. So it will be that ratio. And then what you can do, you see, is you can compute this thing well, let me give a concrete example. The what you can do is you can show that this ratio is in fact e to the integral chi bar of x, let us say, delta x minus y, zeta of y, d fourth x, d fourth y, where delta is the Feynman propagator. Delta of x minus y is an integral d fourth p over 2 pi to the fourth e to the I p x minus y, and then it's minus I over p squared plus m squared minus I epsilon. So there's this minus I epsilon that I was talking about before. And oh, wait a minute. No, I've got something wrong here. This is actually minus I times minus I gamma nu p nu plus m. So I left something out. The Dirac propagator, you know, famously is 1 over a linear form in P. And you may say, well, how do we get that? Well, we get that by using this formula over here, which is that, first of all, that you can shift Grassmann variables and make no change, and then formulas like this, that e to a quadratic form in the thetas plus something linear in the thetas is this expression times a determinant. That's what you use to derive these very last formulas. Once you get this formula, namely that the mean value in vacuum of this time-ordered product of an exponential is just given by this Grassmann-esque expression, you're then able to derive the two-point function very easily, namely, you just differentiate with respect to zeta bar and zeta, and then set zeta and zeta bar equal to 0. And what you then get is 0 time-ordered product psi x psi bar of y 0 is, and you then differentiate this expression, and that pulls down a zeta, pulls down a delta, and in fact you just get this expression here, namely, let's see, to get a psi bar you do d by d zeta bar, and to get a psi bar of y you do d by d zeta of y, then you set zeta equal to 0, that just gives you delta, and so this is just delta of x minus y, and delta of x minus y is that expression there, and often one takes the minus I and puts it out here in front. Okay, I think that is pretty much what I wanted to say. You guys may have questions.
I have a few questions about some properties of Grassmann variables. I think, I know they're in your book. I want to look before I ask though, because it might not be worth it. It's probably answered in your book.
I hope so. If not, send me an email and I'll try to add it in. Well, let's see, I've got one left. Okay, you hungry?
Yeah, okay.
Good, all right, so now I have to go to Costco and buy more of them.
Hey, do you use
the part that I skipped a little bit was this, and maybe I should try to fill that in, kind of winging it though. I don't have my notes on that. Does any of you have any other questions specific?
Not really, nothing off the
All
top.
right.
The only thing, do we not need, if we're going to define it with the Dirac action density in the denominator in that interval, do we not need a minus sign there because we had that and we've sort of been calling that S naught?
Yeah, but we always had a plus I.
Yeah, but why, we have a minus.
The minus is on the H0.
Oh, okay, I see.
The minus on the H0 turns into a plus on the action. And one way of thinking about it is, remember the Lagrangian.
Yeah.
It's the square of the time derivative minus the potential energy. The potential energy has the square of the gradients, and it has the powers of the fields. All occur with minus signs. So minus the Lagrangian is plus that part of the Hamiltonian.
Right, it has to be that way in the Euler theorem because we have what the L infinity one, I think. In physics we don't really care about that, but I think we could write that down somewhere in these Grassmann. This ends up.
All right, so let me
Do you want on
try to
calculus?
explain this. To go from here to here is the stuff that I derived over there. Now then the question is, how do you go from there to there? And I must say I've forgotten the intermediate steps, and I didn't write them down at all.
Let's think about it over the weekend.
Do I need to turn it off?
Yeah, I'll turn it off. What